Very good morning to all of you. I hope you all can see my screen and hear me clearly. Now, in this part of the lecture, we are going to talk about elements of visual perception. We are basically going to talk about human eye. So, let us first look at eye characteristics. The diagram that I am presenting to you is a cross section of human eyes, and we are going to look at different characteristics very quickly. So you can see that it's nearly spherical object. Of course, there are some distortions here and there, but as you know, in physics, we deal with approximations. So we call it as nearly sphere, and it's around 20 millimeter in diameter. Remember diameter. So that means this and this roughly 20 millimeter, slightly less sometimes, but you can take it 20 millimeter. The figure that I'm showing here, it's an average figure over a large population. There are three membranes: cornea, the outer transparent layer, which is here, and the sclera, or the opaque outer cover, which is here. They call it sclera or something like that, the way you pronounce it. And the retina is the innermost, which is the image forming layer. So which is of our important to us as far as the image formation is concerned. There is a optic nerve which comes and starts somewhere here. So at this point the retina is not there. This is typically called as a blind spot. And there is one more spot which is called fovea, and I'm going to show you that this is the one of the most sensitive part as far as human eye is concerned. It is directly opposite to the eye lens. The eye lens can is held on two ends by what is called as ciliary fibers, and they can be stretched on either sides, and when they stretch or unstretch, that decides the size of the lens. So lens can increase in width, lens can decrease in width. It changes in width from 2 millimeter to 8 millimeter. Uh, Sorry, this is about the diaphragm. So the iris decides the diaphragm. So this is the diaphragm size from here to here. It can vary from 2 to 8 millimeter depending on low light or strong light situation. The the lens focal length can again vary. This way width can also vary. So your eyes are most relaxed when you are looking at infinity. When you are looking at short distance, then the ciliary fibers get stretched and the width of the lens changes. Keeping them stretched for a long time affects their performance. It makes them little weird. They get worn out, and that is why the eye defects start. So if you are reading something, if you're watching computer, if you're watching on your mobile screen for a long time, and as we are all doing these days in lockdown, your ciliary fibers are always being stretched for a very long time, and that will lead to their wear and tear very quickly. So one of the ways to relax them is to look at infinity or look at a far distance. So anywhere 6 7 meters and beyond is a far distance for human eye, and your eyes get relaxed. When your eyes are closed, they tend to get relaxed, although they will not happen immediately. For example, if you have half an hour computer exposure and if you close your eyes after that, it will take at least 10 minutes for the ciliary fibers to get relaxed. So closing your eyes for 2 minutes will not help you much. So take care of your eyes because they are very important and they are being overused during lockdown. Okay, let's go ahead. Retina is the innermost membrane. Objects are imagined on the surface. This is the variation of number of light receptors on retinal surface as an angle from the fovea. So let's go to the previous diagram. This I take as 0 degree and then I increase my angle on both sides up to say 80 on this side and say 80 on this side. And this is the region in which the larger number of photoreceptors are there. So light receptors, and there are two types of light receptors as you know from your basic biology class, rods and cones. So let's discuss cones first. So in this diagram, the cones are shown by solid lines. So you can see, and on this axis, it is number of light receptors, that is rods or cones per millimeter square. So imagine how tiny is 1 millimeter. So in an area of 1 millimeter by 1 millimeter, look at these numbers. These numbers are huge: 45,000, 90,000, 1,35,000. So many number of cells are there. You can see that the cones are fairly less at most of the angles, but near the fovea, this number is very large. So near to the fovea, this number goes up to 6 to 7 million, and they are highly sensitive to color. So these are needed for your color vision. They can resolve fine details because each cone is attached to a single nerve ending. So the sensitivity is very high, and that is why you can see things very clearly when they are in different colors. But they are called photopic vision, or cone vision is called photopic vision or the bright light vision, because they are sensitive. They work only when there is a strong light. Why? Because they are less in number. Although the number is very high here, at the rest of the places they are very less. So as the light intensity drops, their efficiency drops quickly. So in the low light situation, you notice it's very difficult to watch colors. So if there is a cloudy sky, colors are not so vibrant. If it's a sunny sky, the colors will look very vibrant. So these are normally needed for the bright light vision. The human eye has another arrangement of other type of cells which we call as rod cells, which are needed for low light vision. So rod cells are more uniformly distributed. Their numbers are large. Imagine that it's a continuous curve. Then the numbers, you can see that it's very fairly distributed. Of course, it dips here at the blind spot, and when the at fovea where the color image processing or color image receptors are very strong. So they give a general overall picture of the field of illumination. They are sensitive to light. They are sensitive to dim light also. So when the light is very poor, you can still see things because of this one. You can't see colors. The human eye is a very efficient system. So it divides the tasks into two different type of cells. So one type of cell takes the job of interpreting colors. Other type of cells take the job of interpreting the brightness. The word used over here is called scotopic or dim light vision. Distribution of receptor other features are this. Distribution is radially symmetric about the fovea. As we have seen, the diagram was fairly symmetric about this point if you take apart from this blind spot glitch. Then in the blind spot there are no receptors, so emergence of optic nerve because the optic nerve ends over there. Then fovea, which is circular indentation in the retina about 1.5 millimeter in diameter, and most of the image formation happens in fovea. The cone density is very high in fovea. And yes, one question we normally ask on present day is how much how much can we compare the electronic sensors with how much we can compare the electronic sensors with human eye. So present day high-end electronic sensors can compare with human eye, not the lower end. So if you have a 12 megapixel, it is still be much less than what human eye might have. But there are sensors which are now in the domain of 50 megapixels, 70 megapixels, and they can compare with capabilities of human eyes. This is a diagram of typically how the image formation takes place. This is an object which is at 100 meter, 15-meter height. This length is around 17 millimeter. That will help us to find the image formation. Image is created inverted. So variable, the lens thickness can change. It's thick for close focus, thin for distant focus. The distance of the focal center of the lens to retina is 14 to 17 millimeter. Varies from situation to situation, what you are looking at. And image of a 15-meter tree would be around 2.5 millimeters. So you can see it's a large tree, but image is very small on the retina. Most of this will be around fovea. Image is almost entirely on fovea, where the sensitivity is very high. Human eye does one more task, which is the brightness perception. So it can perceive a very low light, low intensity light as well. It will perceive a very high intensity light. A low intensity light could be in a dark region, while a very high intensity light can be in a region where, say, a lot of snow is there, or lake water is there, or a white painted building is there, then the intensity is very high. Human eyes can perceive both. So the perception is varies from 10 power minus 10, which is a scotopic threshold, to a glare limit. A glare limit is a very, very bright object. Like as we like sometimes try to look at sun and we close our eyes. So we can't look at sun still, but we can still see very bright objects if we want to. The subjective brightness is a logarithmic function. Remember, the brightness varies from so low to so high that its variation is always logarithmic. So let me go to the next drawing. So here is the subjective brightness, which has been roughly plotted on y-axis, and here the log of intensity, which is plotted on the x-axis. So this is the order, remember. So when you say 4, it is 10 power 4, and which is, say, when you say minus 6, it is 10 power minus 6. So you can see from here to here the order changes by 10 power plus 10. plus 4 to minus 6. So the change in the order is 10 power 10. So the human, if I plot a graph which is a log here and subjective brightness, then it looks almost like a straight line. Well, not a perfect straight line, almost like a straight line. Okay, so that's how the human eye works. But the visual system cannot operate over such a large range simultaneously. Human eyes are not sensitive to entire range from a very less low image to a very high image, high low brightness to a very high brightness at once. Think about it. Suppose you are in a bright sunny day and you enter into a dark room or a dark hall, or if you have been to watch a movie. Now, present day movie watching in a theater is also not that dramatic because most of the time these days are multiplexes. So when you enter the multiplex, you get first a coffee shop and this shop and that shop. And most of these places are dimly lit. You don't go from a very bright area to a very dark area. It takes 4 5 minutes for you to get into the dark theater, and by the time your eyes do adjust. But I do remember those days when multiplexes were very few, and most of those theaters are old single screen theater. I mean, those theater, what used to happen is you get on the counter, buy a ticket. The counter was generally used to be facing the road. So you buy the ticket and you get into the theater, and suddenly you will find that everything is dark. You at least take 4 5 minutes to find your way out, to adjust things. So human eye is not sensitive in all the scales simultaneously. It takes time to adjust. So when your eyes are adjusted, suppose you are in a dark room, your eyes get adjusted to the dark room in 10 15 minutes. You can see many things very clearly. But suppose you immediately turn the lights on, bright light on, then you will find that you cannot see again things very clearly. It will take some time to adjust. So it doesn't it so again it is the efficiency that comes in the picture. So human eye saves itself from uh, decoding all the light data by concentrating on a small region at once, and that it does very effectively. This phenomenon is normally known as brightness adaptation. Then the brightness perception has other issues also. So for example, this diagram which is called Mach bands. Uh, in this is dark gray. This is, and the gray pattern gets lighter and lighter as you go from left to right. Now, intensity in one rectangle is same whether you are look at this corner or this corner. If you're here or here, the intensity is same. If you're here or here, the intensity is same. So the intensity pattern fluctuate like this. But if you look at it as a whole, and try to see it as a whole, you will find that, or you will perceive that this edge, which is close to a darker region, is slightly brighter, and this edge, which is close to a brighter region, is slightly darker than this. So this is your actual intensity pattern, and this is the perceived intensity. So here you feel that it is slightly brighter, so the intensity is more, and then it drops, and here you feel it's slightly darker. So if you look, this will you will perceive. If you focus only on one square, you will not. But if you focus on all the squares simultaneously, then you will feel this variation. You will feel that intensity drops as you go from left hand to the right hand, and your variation is this way. While making the image, it is designed to be this way. So that is the brightness perception that varies in situations. The visual system tends to undershoot or overshoot around the boundary of the regions of different intensities. This is another example of brightness perception. It is called simultaneous contrast. You will find that this is more bright. This appears to be more bright than this. However, all the three inner squares are same. They have the same brightness. Howsoever bright is this, same bright is this, and same bright is this. But their boundaries are different. This is in the darker boundary. It looks much uh, intense. This is in a lighter boundary. Then the same thing looks dark. So again, that is appears that way. I know that is the brightness perception of human eye. And there are other visual perception. You can always see a square which is not at all drawn, but you can see it very clearly. You can always see a circle here which is not drawn. So although these points from here to here don't exist, the points from here to here don't exist, your brain can still draw them. Here both the lines are of same length, but this will appear shorter and this will appear longer. Again, your brain is interpreting. So interpretation is also an issue. All these lines, all these oblique lines in this drawing, they are parallel to each other. But if you look at them as a whole, you will find them that they are not parallel. They are going uh, they are going away from each other at this point and they are converging towards that side. So all these variations will happen if you look at them together. But all the oblique lines are parallel to each other. So the aim of this chapter was to basically briefly understand the human perception of vision and to understand where it is strong, where it is weak, how it can be manipulated. Thank you.